Hi, everyone. Welcome to our second video for week 7. We're going to talk about the correlation coefficient. The correlation coefficient is one way to measure the strength of the relationship between X and Y. The population correlation coefficient, denoted by the Greek letter rho, which looks kind of like a curly P, is computed by using all possible pairs of data values X, Y, taken from a population. And like most population parameters, this is something that's very difficult to calculate because it is impractical or impossible to collect all of that population data. The linear correlation coefficient, denoted by R, is computed from sample data and measures the strength and direction of a linear relationship. So typically, we're going to collect paired data from a sample and use that to calculate a linear correlation coefficient, which will then be an estimate of the population correlation coefficient. There are different measures of linear correlation coefficient. Specifically, the one that we're focusing on in this textbook is one of the most common that is used, and it's called the Pearson Product Moment Correlation Coefficient, or the PPMC. I am never going to test you on that. I don't expect you to memorize that. But if somebody asks, it is specifically the PPMC that we are using in the textbook, and it is the one that the TI-84s and GeoGebra and most other calculators calculate by default when you ask them to run a linear correlation program. So before we talk about how to find it, let's talk about how to interpret it. What does it mean? So that R value, that linear correlation coefficient for sample data, is always going to be a number between plus and minus 1. Values closer to those endpoints, positive 1 or negative 1, indicate stronger linear relationships. So the closer to plus or minus 1, the stronger that linear relationship is. If R is equal to 0, there is likely no linear relationship. That doesn't mean there's no relationship at all. It just means it's not linear. It could be curvilinear. If you end up with an R value that is at those endpoints equal to plus or minus 1, that means it is a perfect linear relationship. All of the sample data lies on that line of best fit. So here's kind of a graph. You can see that middle area around 0 is the no linear relationship line. Again, there could be a relationship, just not linear. And then out near the edges, near negative and positive 1, we have strong linear relationships. When R is positive, it means that as X increases, Y also increases. We would say that there is a positive correlation between X and Y. This also means when you're looking at a scatter plot of X and Y, that the graph has a positive slope, that it tilts upwards. A negative R value means that as X increases, Y decreases. The variables change in opposite direction. And we would say that X and Y share a negative correlation. If you were to graph X and Y, that graph would have a negative slope. It would tilt downwards. The sign on your R value should be the same as the slope in your regression equation. And remember that that's the value that's in front of the X. The slope times X. So whatever's in front of the X is being multiplied by X. That sign should match the sign on your R value. So we see a couple examples here of what a graph looks like for specific correlation coefficient. So the top row, you can see all of those graphs tilt upwards like a hill, and they all have positive correlation coefficients. This first graph is R is equal to 0.5. So there's a loose correlation. It's roughly linear. but there's definitely a pattern here. It tilts upward very clearly. I can see there is some relationship between X and Y, whereas X gets bigger, Y gets bigger. At R is equal to 0.9, those points are much more closely packed together. That linear pattern is much more clear. And then at R is equal to 1, those points all lie exactly on that same line. We can see down in the bottom row, we get a similar pattern. The only difference is because those correlation coefficients are negative, that matches that slope in the graph where all of the graphs are tilting downward like a slide. They all have a negative slope. Okay, so let's talk about how to find these correlation coefficients. If you are on the TI-84, you're going to go stat, edit, enter your X values in L1, Y values in L2. You're going to call that same linreg A plus BX that you did for the regression equation. X list is L1, Y list is L2, frequency list should be blank. And that regression equation, if you want to store a variable there, you can. However, you may run the linreg function and not see an R or an R squared value. If that happens, you need to run diagnostic on. So I'm going to pull up my TI-84 so you can see what that looks like. So let's go back to our home screen. To run diagnostic on, we need to open the catalog. And you'll notice above the 0 button in blue, it says catalog. So I'm going to press second 0. And that opens up the catalog of all the function calls in your calculator. I want a function called diagnostic on. It starts with a D. So I'm going to find the button that has a blue D above it, or in this case, a green D. And that's right above the X to the -1 button. So I'm going to push that. And you can see it takes me to the D list. And then I'm going to scroll down until I see diagnostic on. So we can see diagnostic off. Diagnostic on is the one we want. And once your cursor's at diagnostic on, you're going to click enter. And then you're going to click enter again to run the program. Once you've done that, when you run that linear regression function, it should output an R value. For GeoGebra, a little bit more direct. You create a list of ordered pairs, just like you would for the fit line. Curly brackets around the list, and then each point as an ordered pair. And then you're going to call the correlation coefficient function, which is correlation coefficient. So correlation coefficient, and then your list name. So we're going to do 2 examples, going back to those examples that we found in the first video. So this was example 12.6, where we're looking at statistics student, and we're comparing their 3rd exam score to their final exam score and looking for a relationship. So let's pull back up our TI-84. And we know the first thing we want to do is make sure that data is in a list. So I'm going to press stat, enter, and you can see that the data is in the list from the last time we did this. Next, we're going to go to stat. We're going to go to calc, and we want option 8. L1, L2, I'm not going to worry about storing any things I don't need to graph. We did that last time. Calculate. And we see that A and B from before, and then an R squared and an R. So the correlation coefficient that we're being asked for is just that R value. Typically, you're going to see me round my R values to 4 decimal places, just like we did with probabilities and p-values. So I would record this R value as R equals 0.663, and then 09 is going to round up to 1. So I see two things from this correlation coefficient. First, it's positive, if I could spell today. So I know that as X gets bigger, Y is also going to get bigger, meaning students who did better on their third exam score likely also did better on their final exam. There is a linear or roughly linear relationship between third exam and final exam scores. You did better on one, you likely did better on the other. The other thing is I see a value that's slightly bigger than 0.5, meaning this is a loose linear relationship. It's not super strong, but that's fairly confident that there is a clear relationship between changes in X and changes in Y. I expect that if Y or X goes up, Y is going to go up. You're going to see me do something in future videos. You'll notice that LinReg spits out a whole bunch of information. Typically, when you run this to find your regression equation, you just copy down all of these values. A and B form the regression equation. Both R and R squared are useful. So at this stage, I'd also write down that R squared value, which we're going to talk about in a minute. So R squared is 0.4397, which we round to 4 places. And we're going to talk about what that means in just a minute. Okay, let's go ahead and try another one. We're going to do the try it example, 12.6. So this was the scuba divers, talking's hard today, where we looked at depth in feet and maximum time in minutes. And we used GeoGebra for this. So I'm going to pull our GeoGebra screen back up. And you can see our data from last time. So we have our list of data points. And then we have that fit line equation. And now we want a correlation coefficient. So I'm going to call the correlation function. And then I need that list name where my data is, which is in list A. And this one you'll see gives us a much bigger value. So here we get R is negative, but that decimal is bigger, 9,629. So this is a much stronger linear relationship. The data is more closely packed around that line of best fit. So I know that that negative sign tells me my data has a negative slope. So as that depth in feet gets bigger, the maximum dive time should get smaller. Those variables change in opposite directions. So I know as X goes up, Y goes down. I also know this is a fairly strong linear relationship because that's pretty close to -1. We should also write down R squared. We're going to find it a little differently. R squared does literally mean take that R value and square it. We want to minimize rounding error. So instead of using this rounded decimal, I'm actually going to grab A, which you can see is the saved value for the correlation coefficient, and then I'm going to square it. And as a comparison, if I were to do that with that negative 0.9629, whoops, I didn't mean a decimal point there. It's the first decimal points are close. We get a 927 and a 927, but here we've got a 25, which is going to round up to 3. Here we've got a 17 that's going to round up to 2. Sometimes that difference will be more or less pronounced depending on what that original value is. So it's not horrible if you forget to do this, but it is generally better to record the value as exact as possible. So I would write down this unrounded value squared, which is 9273. Okay, so my hope is that doesn't feel too scary. Let's clear that. Now we're going to talk about what that R squared value means. And that R squared value is called the coefficient of determination. And like we saw on the last slide, it is literally the square of the correlation coefficient, R times itself. What that represents is the percent of variation in Y that can be explained by the variation in X. 1 minus R squared, or the complement of the correlation or the coefficient of determination, represents the percent of variation in Y that's not explained by the variation in X. So a bigger R square value indicates a stronger relationship between X and Y. And the bigger R squared is, the smaller that 1 minus R squared value will be. So we're going to do this for the two that we saw here. I'm going to really quick just grab our calculator and do the rounded squaring because I think that's easier and I'm lazy. So second clear. So for that first 1.6631 squared, and we get something close to what the calculator gave us last time. So it's giving us 0.4397. And then we're going to try it down here and then talk about what those numbers mean. So the next one was negative. We need to put that in parentheses, negative 0.9629. And we get that 0.927 rounded. It's going to be 2, a little bit smaller than what we saw last time. 9272, that's the rounding error. So this is telling us that in the first instance, where we have a smaller R value, I'm having computer issues here. So here we have a smaller R value, meaning that relationship between X and Y is not as strong. This R square value tells me that changes in Y, only about 44% of the changes in Y are due to changes in X. So that means there's about 56% of changes in Y that are due to changes in something else. And in this sentence, I'm using a symbol here. That's called the Greek letter delta. It does look like a triangle, and that means change. You may have seen it in a science class. You see a lot in things like chemistry and physics when we talk about changes in quantities. So 44% of change in Y is due to change in X. Whereas for that second example, we had a really strong linear relationship, 0.9629. And in that case, almost 93% of the change in Y is due to a change in X. Meaning 7% is not due to changes in X, it's due to something else. So this allows us to see how that change in X is affecting the change in Y. The bigger that R squared value, the more responsible X is for changes in Y. Okay, that's it for this video. If you have questions, let me know. You can contact me via email, drop in by office hours. I'll be having office hours Tuesday night, Thursday in midday and at night, and then Friday, I think in the late afternoon. And again, Friday is that last day to get work in for week 7. I hope you have a good rest of your week, and I will see you in our next video.